Okay, so today we're going to learn a quantum algorithm to search for an AES key given a single sample in square root time of what is normally expected in classical computing. All right, so quantum key search for AES in square root time. Okay, that's what we want to do. So for example, if we are dealing with 128-bit AES, a brute force attack would take 2 to the 128 if you are given just a single sample and assuming you can't do any differential attacks and all those things. So when you are given a single sample, there is no other attacks other than brute force trying every key, right? And then whichever key, so you're given a single sample in the sense you're given an M and AES, a ciphertext which is AES under that key of M. Okay, so you're given one sample of a plain text ciphertext pair. All right, and so you could search for K, but it'll take you time 2 to the 128. You can go through all of them. All right. What Grover's algorithm will show that you can. So this is the major innovation of Grover. Okay, Grover's algorithm will find K with high probability in time square root of 2 to the 128. Okay?
Isn't that 264?
Yes. All right. Which is almost feasible on modern computers, right? Given the fact that we can do 2 to the 80 hashes nowadays, all right, with all this Bitcoin hash thingy. So this is why we have moved on to 256-bit keys for AES, given the threat of quantum computers, because then the attack would still require 2 to the 128 time. All right. So right now we're going to see how this is done. Okay. So the first thing is that we are going to prepare a quantum state with all 2 to the 128 keys in superposition. All right. So there will be a single state and which will be 128 qubits. Okay. So this state will have 128 qubits. All right. So basically the state will be sigma over all k k belongs to 0, 1 to the 128. Right? All binary strings of length 128, those are the keys. So we're going to have superposition, and this is normalized, so each coefficient is the same. Right? It is if you can think about it, let's give this a name here. All right, let's call n equals 2 to the 128. Okay, typically it's written as 2 to the lambda, where lambda is the security parameter. All right, so lambda will be 128, and capital N is the exponential of that. That is the number of different keys. So as you can see, this is normalized by putting a 1 by square root n there. All right, because then probability of each thing is 1 by n, and then you add them up, there will be total probability 1. Okay, so that's the state. I mean, you can push this inside, right? I have written it this way or that, doesn't matter. Right? You can put it inside the summation. Right? Probably better to write it like All right, so the first question is, how do you prepare this state? Okay, so maybe we'll do that on that board. Let's just go over the big steps first. All right, let's assume you can do that. All right, you can prepare a state like this where all the keys are in quantum superposition. Okay, so now what we're gonna do is we're gonna also attach to this state some ancillary state. All right, so for example, we will have this tensor product with working state. Okay, howsoever many qubits that we need. Okay, so those will be in extra qubits. Okay, so these are additional qubits or ancillary qubits. Okay, so what you do is you have your sample M and C. All right, what you do is you set working state to just M. Okay, so encode in that working state just that single M. All right, the message. All right, so it will be, since M is 128 bit, this is also 128 qubits. Okay, so then we can call this working state, let's say W. All right, so right now our state is, and since we can write this as a tensor product of two things, they are not entangled. All right, these are some qubits, those are some qubits. We are looking at the net 2 times 128 number of qubits. All right. All right. Now there will be some. I would say we would need some more qubits. Okay. Because what we are going to do is we're going to run a very simple quantum algorithm. On the working state. And what this does is on working state and psi. Okay. So if you think about it, right now we have psi tensor W looks like this. Okay. So because that single M is attached, is like, in tensor product with all the other state. All right. So I could have written it like this, but I just took the M inside. All right. So one way to think about it, it was really this, right? Because that's it, tensor product. But you can write this as summation 1 by square root n k comma M. Okay, which is a total of 2 lambda qubits. All right. So what we do is now compute AES k of M into another lambda qubits. Okay, let's call it O. Okay, so we start with, O equals 0, 0, 0, 0, like 128. Okay, so we have 128 bit. Those are in superposition. These are not in superposition, single, and that's also single. And now the magic of quantum computation is when you say you run some algorithm, it happens on all the superpositions in one shot. All right. So what will happen is with that AES quantum computation, your final state would be psi w, and this guy would be AES under K of M, and we should open this up because now things are entangled, if you notice. Okay. Okay, for the kth superposition, what is sitting here is M evaluated under K key. Okay, we can basically ignore this guy at this time. All right. So that's where the entanglement. This quantum computation ended up causing an entanglement. How long did this quantum computation take? It takes as much time as it's time take to evaluate single AES. Okay, let's say AES takes some polynomial in 128. This is 128 bit, some polynomial. So it took time, quantum time equals poly 128. Right? Maybe it was quadratic or something, however time, Actually, it's probably, yeah, let's call it polynomial. It's quadratic or cubic. There are some multiplications involved.
Yeah.
So in polynomial amount of time in 128, you manage to compute this thing.
Mm-hmm.
All right. Now what you do is, you run another computation. Is it still coming in? Yes. Where you check if C is equal to AES Kn, where C was your
C
given
was the original.
ciphertext. All right, and so you can compare these qubits with a constant cube set of bits. All right, so that's just a simple quantum computation. So the result will be the bit. So you put it as 1 by square root n k w this one you can call it check bit. All right, and then there is of course the AES K. But this is the most important thing. We can literally ignore these qubits now. Okay, that check bit is 1 only in the proper K. All right, because we can assume that AES this property that given C and M, there is just going to be one unique K which suffices. I mean, it's possible that there are other keys. By the way, AES does not rule that out. All right. But it will be very few such keys. In case that is the case, you may need a few more samples. That will positively tell you that this is the key. Right? AES by itself does not guarantee that there is a unique key for each C and M. All right? Yeah. AES guarantees are more like you can't find K. All right?
Okay.
It doesn't, and also it's a permutation. That for any particular K, for every M there is a unique C and vice versa. Right?
Yeah.
So those kind of guarantees are there, but it doesn't say anything about a particular C. We're going to clean up and write over here what state we have. All right, the state we have is essentially sum over all keys, the K key, and the check bit. All right, and we are going to ignore all the other bits. They can be lost for all we care. Right, so this is all we care about. And the property is that check bit is equal to 1 for the correct K. And if and only if, right? And it's 0 for incorrect K. And like I said, it's possible that for some incorrect case it may still be 1. But if that's the case, we have to maybe try few more samples, because then you'll be assured that there is just one key which worked. All right, you could have done this whole thing with some extra M1, M2, M3, or 3 or 4 of those guys, and did the whole experiment like that together. All right, so for the moment we'll assume that there is just one K for which check bit is 1, and for all others it's 0. Okay, so how does this help us find the particular k for which this check bit is 1? Well, it's like we are in a horrible situation because the density for this correct bit is like really tiny, and the zeros, all the other guys are sitting with 0, all right? So if you did a measurement of just the check bit, it will most likely give you all the bad guys, or one random guy from the bad guys, all right? You will not get the good guy, all right? So this is where the Grover magic comes in. He's gonna show how you can transform it so that most of the probability density comes to this guy, the good k, and all the other gets together get like tiny things, right? In fact, he will show, okay, so this is the major step 6, okay? It's called the diffusion step. Okay? The ultimate aim is for the k where check bit is 1, we want the amplitude, which is sometimes also called the coefficient of that superposition, right, to be 1 by square root 2, okay? So that if you measure just that one thing, okay, then with probability half, you will end up in the projection which will give you the k, and all the others will be gone. Okay, so when you do the measurement, you will be in a projection state, right? And the projection state will be 1 with probability half. Okay, so with probability half, but when you are in 1, you are attached with just that one particular k. And for 0, you could be attached with any of the other cases. So net, the 0 guys will have probability half, and the 1 guy will have probability half. But the 1 guy is only attached to your good particular key. And the 0 guys are attached to all the other keys. So with at least probability half, you would have found the key. All right? So that is what we wanted now. With high probability. So with probability half is good. You can repeat this experiment, all right, multiple times, and then with exponentially high probability, you will get the key, all right? So this is the idea now. How do you go from this horrible distribution to this distribution, all right? So that is the essence of this algorithm, okay? So the diffusion step is the following idea, all right? So we will assume that we can compute any unitary transformation, okay? And I think we discussed earlier, not in this lecture, but in a previous lecture, that you can build any unitary transforms from small 2 by 2 poly matrices, all right? So for now, we'll just assume that you can compute any unitary transform, all right? In fact, now, if you notice how many qubits are there, there are lambda qubits here of 128, and there is 1 qubit, all right? So we're looking at unitary transforms. So although the qubits are lambda, the number of states is exponential, right? Which is as good as k. So the unitary transform will be a capital N by capital N matrix. Okay, if you are just dealing with unitary transforms corresponding to states of the first lambda qubits, right? Okay. So for example, right, just as an example, right, suppose lambda was just 2, okay? So there are, then n is 2 to the 2, that's 4. Okay, so for example, you could be in a state which looks like 0, 0, plus 0, 1, plus 1, 0, plus 1, 1, right? A unitary transform takes any state which is in the vector space corresponding to 0, 0, 0, 1, 1, 0, 1, 1. All right? So you'll take that, you will multiply it by a 4 by 4 matrix and you will get a new set of coefficients. Right? So whatever the coefficients of these guys were, the unitary transform is work on the coefficients. Right? Here the coefficients are all 1, 1, 1, 1 or 1 by 4, 1 by square root of 4, right? 1 by, 1 by 16, right? Each coefficient is 1 by 16 for square, yeah. A square maybe, 1 by 2, okay. Right? So all the coefficients are half here, right? So the probability is 1/4 square of that. Okay. So normally it's 1 by root 2 when there are only two things. As this is 1 by 2 in each. So the total density will be 4 sums over 1/4. All right. But anyway, the main point is that this is the unitary transform. All right. And the property of a unitary transform is that HU is equal to I. Okay, where H stands for the Hermitian transform. If U is actually a real matrix, then it is just, U transpose U equals I. Okay. So now we are looking at, since our lambda, okay, we are looking at n equals 2 to the 128, okay, and so unitary transforms of n by n matrices, okay. Now this sounds humongous, right? Mm-hmm. But that's the beauty of the quantum computation, that it's working on all the things in parallel, okay, 2 to the 128 things, all right? So it looks not humongous. So for example, you could think of a Fourier transform. We deal with Fourier transforms on really tiny things like, 2 to the 16 or 2 to the 8. Here we're trying to do a Fourier transform 2 to the 128. In a single quantum step, you can do that. Boom. All right? That's where the magic comes. All right? So basically, now what we're going to do is we're going to apply some unitary transform on the state to achieve what is called diffusion. All right? Like we said, the diffusion has to have the property that one particular state is going to get it's going to accumulate all the probability density, and all the bad states are going to get really much smaller, right? Mm-hmm. So that they effectively are not very useful. So how do you go around doing the diffusion step? So this is the diffusion metric. Okay. So, I should pre-warn you that we will have to do this step square root n times. That's why the complexity is going to be this. Because so far the complexity was polynomial in 128. This is where it is almost exponential, but it's sub-exponential. It's 2 to the 64. All right? But we will see what is a single transform, and we're going to repeat it square root n times to achieve this goal. All right? What the single transform does is the following. It has this property, but it looks like this. It is minus 1 plus 2 by n, and 2 by n, 2 by n, and along the diagonal it is all minus 1 plus 2 by n. Okay, and these are all the other entries are just 2 by n. Okay, this is the diffusion matrix, and we will check right now that this is actually a unitary matrix. All right, because if it's a unitary matrix, then we can use quantum computation to apply this. Right, and as we saw, we can do it with 2 by 2 transforms, and there'll be just some, small number of steps. Okay. Logarithmic in n. Okay. So there'll be like Pauli in 128. That many steps you can do it. So why is this a unitary matrix? Okay. So we have to check two properties. Since it's a real matrix, all we have to check is that the U transpose U is equal to I, which is effectively saying that the norm of each column is 1, and all columns are orthogonal to each other, all different columns, right? Because when you take its transpose, this column comes here, and the next column comes here like that, right? For it to become an identity matrix, each column must norm inner product with itself to be 1, and each column which is separate or different from its index, they should all inner product to be 0. So these two properties you have to check, and I will probably not bore you, it is actually true. Okay, so it has been carefully designed that this is a unitary matrix. It's a very simple arithmetic. I mean, for example, you will be checking, right, that this, let's say, this inner product with itself, all right? So you'll be checking if -1 plus 2 by n square plus 2 by n square plus da 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 2 by n square, and okay, is equal to 1. All right? So that is nothing but there are n minus 1 of them. Okay, we can open this up. There will be 1 plus 4 by n square minus 4 by n. Okay, and this term would be 4 by n minus 4 by n square, which is equal to 1. So it was a very easy exercise. And similarly, you can check that the inner product of any two columns. Similarly, you can check that the inner product of any two columns goes to 0. Right? Okay. But you're going to say that this matrix looks very symmetric. How is it going to help us determine that one good guy? So this doesn't sound like this is going to do the diffusion trick. Right? It's just a symmetric matrix. It's going to keep all the amplitudes, which are all same to start with, they will remain same, all right? So the trick is, let's call this the matrix D, okay? We're gonna apply D times another matrix, which is 1, 1, 1, 1, but there is a single -1 somewhere. And that -1 is supposed to be where our guy is. We don't know where it is, okay? So,
That's a guess.
we're not going to guess. What we have is that check bit is on. We're going to do a small quantum computation which will say whenever the check bit is on, negate the coefficient. And for all the others, keep the coefficient. This is exactly what this guy is doing. All right? Remember, this works on the coefficients, these matrices. So currently all the coefficients are 1. All right? If you manage to apply this transform, that one particular, if we could distinguish where it was, all right? So what we would need is a transform which takes 0 to 0 and 1 to -1, 1. Okay? And I claim that's a unitary transform. because look at its matrix. All right, it will do 0 to 0. That's the unitary transform. We'll take the 0 state to 0, and the 1 state to coefficient minus 1 in the 1 state. All right. So if you apply this tiny unitary transform just on that single bit, not on the whole thing. All right. And these, remember, these are entangled. All right. So you apply this on that single qubit. What it will do is it will flip the coefficient or negate only that particular combined qubit superposition. Right? So that superposition will be -1. So which are effectively going to do this. Okay, every state which the check bit was 0 will remain 0. That one particular state where the check bit was 1 will be negated. And now you're applying, after doing that, you apply the diffusion step. Okay? So this will do the magic of concentrating stuff or the probabilities into that particular index or the key. All right? And then if you repeat this square root 10 times, then it would have accumulated up to 1 by square root 2. Okay? So we're going to check that now, why this works. All right? So maybe I'll do it over here. Step number 10. All right? So we're going to, so right now let's assume that we have this matrix Di or D prime. Okay? Which is that matrix -1 plus 2 by n. Okay, but there is one column here where it is actually negated. All right, so it is -1 minus 2 by n, and all others are still, you know. And now we don't have to worry about which I it was, because we did this magical trick that it magically just changed that guy where the check bit was 1 to be that column. All right, because we performed this transform first on that single qubit, and since they're entangled, the combined states coefficient. All right, this is a very tricky thing. I mean, it is very perplexing to people that this combined coefficient is actually a product of their individual coefficients. Right? You would have thought that this has its own coefficient and that has its own coefficient. All right? But whatever their coefficients are, they are multiplied together and kept as a combined coefficient. All right? Because it's a vector space over complex numbers. All right? And then the complex numbers work as scalar products into this thing. And that is what causes this effect. All right? Now, it is quite feasible, I mean, this is very speculative, that there may be even more advanced stuff going on in physics. Okay? Where we can do some extra magic even beyond this. But nobody has discovered that yet. Okay? So for example, a lot of people claim that, you know, there are some quantum gravity effects in our neurons and stuff like that, which allow you to do even more quantum steps. Right? But that's not the subject of this lecture. We'll stick to the magic of currently known quantum physics. All right? So now we have this thing. So let's see what effect it has on the amplitudes. Okay? So as a step one, we'll assume that all the amplitudes are same, which is 1 by square root n. All right? And then let's see, did it do anything good for our particular k? All right? So if you notice, so let's call the coefficient in step j of k. Okay? Remember, k is going over all the 2 to the 128 things. And when j is 0, that is the initial state. All right? And so C0k is 1 by square root n for everything. All right, same. But let's see, if we do one step of this, does our particular k get slight benefit? All right. So for simplicity, so let's take we are going from C0K, this combined set over all K, to C1K, all right? It is this whole set of coefficients, okay? Good, okay. So what is the contribution? So the way to look at this matrix multiplication is, as Bob Monti always tells us, is to view that as a column. That's the contribution that particular index is sending to all other guys, all right? So all the guys are 1, except one guy is -1. The guys who are 1, they are sending k such that coefficient C0K is 1, all right? Contribute this kind of a column, right? 2 by n, 2 by n, and there is this. All right, and this -1 plus 2 by n is at the exact index, whatever that k is, all right? So that guy's contribution. Whereas if coefficient C0K is -1, it's going to contribute just the negation of this, right? Right, so it's going to contribute the negation of it. So let's see what C1K for K belonging to the bad set. Okay, so we'll call the bad set as all the guys which are not the correct keys, and the good guy is the correct one. So let's see what C1K is, right? So it's going to get 1 by square root n times 2 by n from all the guys, okay, plus -1 plus 2 by n from itself, okay, so it's going to contribute to itself, -1 plus 2 by n, and it's going to get -2 by n from that one good guy, all right, so that good guy is going to send -2 by n here. So if you do this summation, it will be, we can call this, actually this is capital N, all right, should not write small n. These are all capital N. Here it was correctly written. At some point I switched to small n, but these are all capital N's. All right, so this is n times 2 by n -1 minus 4 by n. Why is it -4 by n? Because I already counted plus. Okay, so cancel that and then subtract another 2 by n. Right, so net this is 1 by square root n. Okay, 2 minus 1 would be 1 minus 4 by n. So as you can see, it went from 1 by square root n to slightly less than 1. Okay, let's see what happened to the good guy. Okay, and we can call that guy K star, good guy. Okay, K star, good guy. Okay, so it will get, again, we'll get 2 by n from all the guys. Okay, but it's gonna get -1 times -1 plus 2 by n from itself, okay, because it was negated, and that's it, right? So that adds up to two plus 1 minus 4 by n. That is a big jump. Okay. So everybody else, if you notice, everybody got reduced by 4 by n, and basically, although we have to deal with the squares of amplitudes, so it's not that obvious, but you can see that that was going down, so it already increased to 3 by square root n instead of 1 by square root n, all right? And if you notice, if you do it square root n times, that 3 is incrementing every time by about 2. And after square root n time, it will be close to 1. Actually, it will come out to be 1 by square root. Okay, so now finally we'll just double check that if we did this step square root n times, which Bob Filauer mentions, takes 2 to the 64 sequential steps, which is a lot, but it's better than 2 to the 128, right? So we will check that with square root n iterations, C square root n k star will be 1 by square root 2. Okay, so for our particular good k star, its coefficient is 1 by square root 2, and then if you measured the check bet at that point, then because that's the only one which is 1, with probability 1 by 2, you will end up in that projection of that state, which will give you the k star in the other qubits, and then you can measure then each one of them one by one, right? Because they are forced to be that particular k star.
Yes.
Right. So that will resolve it. So now we just need to check that this is indeed the case. All right. That in square root n times, this will become 1 by square root 2. So there's an easy recursion relation from step to step, which will make us prove this very easily. All right. We saw a little bit as to what happened in the first step, but because the diffusion matrix is the same, this d times that thing, so it is essentially doing the same thing. It's not difficult to see that Cj k star is equal to Cj minus 1 k star, okay, plus Cj minus 1 k prime plus Cj k prime. Now this may sound a bit of a complex equation. First of all, k prime is any of the other guys. Okay, take any one of them because they're all symmetric in the other guys, so their coefficients are all the same. So let k prime be anything other than k star. So I'm claiming that this recursion relation holds. All right, and we can first check it for the initial case. All right. So what it is saying is that the coefficient, the new coefficient of the k star guy is the old coefficient of the k star guy plus the old coefficient of other guys plus the new coefficient of the new other guys. All right. So that's kind of interesting. So basically, the increment from the other guys is actually this quantity. Right? That is the additional gain. Okay, so it's kind of increasing itself by additional time. So is there an easy way to see this? All right. That actually follows by just doing the same logic as we did for the first step. If you notice that this quantity can be written as 2 by square root n plus 1 by square root n 1 minus 4 by n. Okay? And this 2 by square root n can be divided as 1 by square root n plus 1 by square root n. So this good guy is the bad guy plus 2 by square root n, and that 2 by square root n has two portions, 1 by square root n, which corresponds to this guy in the previous step, and 1 by square root n, which is corresponding to this guy in the previous step. Remember, in the previous step, everybody was 1 by square root n. All right, and that same logic continues. You can double check this, that this is actually the case, all right?
You just demonstrated it from 0 to 1.
But it also, because the thing is linear, this unitary matrix, it is going to do the same logic. I can give a formal proof, but in brevity of time, we will not do that. All right? And there's also paucity of space on the board. So we will skip that step. But this is the idea. All right? All right. So how does it accomplish our goal? All right? So what it is saying is, if you write this iteratively, that Cjk star is C0 k star, its initial term, okay, plus 2 times C0 k prime plus 2 times C1 k prime plus all the way C to the j minus 1 k prime 2 times plus this k prime. All right. If you follow this recursion relation and you expanded it, you will get this. Okay. So essentially, alternatively, you can write this as at this point, it actually is not even relevant what this thing is, because this is what is going to contribute to maximum gain to us. We just need to make sure that each one of them is at least some quantity, all right? So that when you sum up, it's, so I mean, ideally speaking, if every time you just got 2 by square root n extra, all right? And it is already as a factor 2. So if every time ck prime L is more than 1 by square root n, then after square root n summation, that will contribute 1. All right? So this is what we need to conclude. So we want to prove that CL k prime, okay, is close to 1. Technically, it's 1 by square root n. Okay? So then, since you're summing over all up to square root n times, so this will give you a 1 factor there, right? There may be a 2 here because of this, right? But more or less the order is the main idea, right? We get the correct order here. So we need to confirm that each of these bad guys is not too small, because remember, these are the bad guys coefficients. We want to make sure that the bad guys coefficient didn't get too small, because then they are not even contributing, all right? But we can show that as long as the good guy isn't too big, the bad guys aren't too small, okay? If the good guy is already 1 by square root 2, we don't even care, all right? But if the good guy is less than 1 by square root 2, we can show just by counting that, and since all the other guys are symmetric, that all the other guys have at least 1 by square root n.
Together.
Yes. No, individually. This, remember, k prime is individual. Okay? So essentially, like, remember, everybody started with 1 by square root n. So now, okay, so technically it won't be 1 by square root, because it's decreasing a little bit.
Yeah.
But that's that 2 in the denominator. So it'll go down very slowly. But all of them will be at least 1 by 2 square root n. All right? If you think about it, if we added a square root n of them, they will add up to half, because it is 1 by 2 square root n. And this guy will be half too. But of course, we are ignoring that there's a square term, but it essentially works out. All right? So this is the main crux of the argument. So to complete the argument, we can do it over here. So we have to show that CLK prime is greater than or equal to 1 by 2 square root n for L such that CLK star is less than 1 by square root 2. Okay? So as long as that guy is less than 1 by square root 2, these guys are still have something left in them, right? Because they are contributing that. In fact, 2 times that they're contributing. So this is actually an easy exercise because at any point, you know, the norm is 1. Okay, so we have summation CLK prime square plus where K prime not equal to K star plus CLK star is equal to 1. Okay, because that's a guarantee that that's okay. And so this is about n minus 1 of them. Okay, so since they're all equal,
Square
okay,
dropped
this is
off.
square.
Yeah, square, 1/2. Yeah.
So that would be 1/2. So I guess it was a square root 2 here also. And we actually showed it.
Okay.
Capital N and n minus 1 and n are almost the same, right? Because n is exponentially. So that concludes the proof. Then we can put a QED here. Any questions? I bet you have many questions, but you're not asking.